I'd like to start off the day by having everyone look at two numerical response questions that appear in your worksheet booklet. Questions number 85 and 86. I'll give you about 3 minutes, please, to do these two questions, and then we'll take a look particularly at number 85, but number 86 as well if you have any trouble with it. First thing we notice when we see question number 85 is this centimeters. We got to convert that to meters, of course. Let's draw attention to that. We also see the word suspended. That's an important word because when we see the word suspended, we know that we're going to set two forces equal to each other. Which two forces for number 85 do I set equal to each other? Good? Good. The magnetic force and the gravitational force. So we're going to say Fm is equal to Fg, or you could do it the other way around if you wanted. Fg is equal to Fm. We've got ILB is equal to, well, normally at this point we'd say it's equal to m times g, and it is. But in this case, we already have the value of mg. We have the weight, which is the force of gravity. We know that Fg is 0.389 newtons. If we're looking for the value of the magnetic field, now all we have to do is say 0.389, the gravitational force, the weight, divided by I times L. We make sure that we plug in the value of the length as 0.50 meters. If we do that, we get an answer for number 85 of 3.11 Tesla. Now, there's no exponents to that. There's no scientific notation to that. We see this answer, we can be pretty confident that we're correct on it because they're not asking us to express it in scientific notation. We know that we're going to have to get a number that looks something like this in order to express it, if we can't put it in scientific notation, that is. Question 86 is even more straightforward than this one. We do have to be careful of some units again. 75 centimeters is going to be 0.750 meters. We want to find the value of the magnetic field. We're going to say F is equal to ILB. And we'll rearrange it to solve for B. It becomes F over I times L. Plug in our numbers, make sure we make it 0.75 meters. And when we do the math on that one, number 86 works out to be 7.78 times 10 to the negative something. What was the exponent? Negative 2. 7.78 times 10 to the negative 2. Now, they want that expressed as a B, just as the base. So how am I going to express that? Right. Put the decimal point in there, 7.78. If it said A decimal BC times 10 to the D, 10 to the negative D, we'd express it as 7782. Good? All right, there's two little things that I want to go over here today with you. That will finish up the unit for us. Tomorrow we'll spend a little bit of time reviewing those topics, and then of course on Monday we'll have our test on all these topics. The topic that I want to look at first today is a topic that we call the generator effect. We learned very early on in this unit that Ørsted made a discovery in 1819, a really important discovery, and that discovery was that electricity generates magnetism. When you have moving electrons, whether it's through a wire or whether it's just through the air, we get a magnetic field generated every single time. Well, the generator effect says that we can get electricity produced by magnetism. It's the opposite of what Ørsted taught us. Electricity generates magnetism. Now we're saying that magnetism generates electricity. The generator effect, also known as electromagnetic induction, was discovered 12 years after Ørsted's discovery. It's not a long time. Okay, the very first relationship between electricity and magnetism in the first part of the 19th century. Then this complementary discovery was made only 12 years later. This is a big deal as well. We talked about Ørsted's discovery and how important that was. This is just as important. This electromagnetic induction, this generator effect, is the fundamental basis behind almost every watt of electrical power that's generated and then comes to our houses. If we didn't know this, we wouldn't be able to cook our food on a stove. We'd be out in the backyard cooking our supper on a fire. We wouldn't be able to read a book by a light. As soon as it got dark, we'd be going to bed. Now, we talked about Ørsted in his discovery that electricity generates magnetism. There were no conditions on it. It happened every time. If you had a single moving electron, it would generate a magnetic field every single time. The complement to this, the generator effect, the idea that electricity is generated by magnetism, doesn't happen every single time. There's a condition that must be met in order for this to happen. There's actually 3 conditions, but we only need to meet one of those conditions in order to make this happen. The first condition, assuming we have a wire and a magnetic field, the wire's got to be moving. So you got a wire, you got a magnetic field. You move the wire through the magnetic field, that wire will have a current induced in it. You're going to get a potential difference in an electric current produced in this wire. The second condition is exactly the opposite. You got a wire and you got a magnetic field. Let's this time move the magnetic field. Move the magnets relative to the wire. Somebody in the last class asked me, it was a good question. He said, well, what if you move both? Well, if you move them both at the same speed in the same direction, what do you think is going to happen? Nothing. You're not going to get a current induced because there's no relative motion. The important thing here is not which one is moving. The important thing is the relative motion between the two. If you have relative motion between the two, you're going to either meet condition 1 or condition 2 or a combination of both, and you will get an electric current generated. If you don't, then you're not going to get any current generated. Now, the third one's a bit different. The third one is changing the magnetic field. If you change the strength of the magnetic field, make it stronger, weaker, then you're going to produce an electric current as a result of that. We'll focus on the first one. When we move the wire relative to the magnetic field. When we focus on that, however, understand that the second one works exactly the same way. The same analysis really applies. It's just helpful for us to look at one. The third one works on a bit of a different principle. We won't really talk about that. You just have to know that a changing magnetic field does cause an electric current to be generated. When we do move that wire relative to the magnetic field, electrons start moving. And we'll talk in just a minute about why those electrons start moving. But for now, just trust me. The electrons start moving. If you've just got a wire like this, then those electrons are going to start accumulating at one end of the wire. You're going to get a buildup of charge at one end of the wire. That's going to give us a potential difference. It's going to give us a difference in energy per coulomb between one end and the other end. If, however, this is connected to an entire circuit, maybe into a light bulb right there, then the electrons are going to start flowing all the way around that circuit now. They're not going to just accumulate at the one end of the one wire. They're going to keep going around, and they're going to power that light bulb. Or power whatever it is that you have connected to the circuit. Let's take a look at exactly why this happens. Why we get electrons starting to move, why we get an electric current as a result of having this magnetic field. Let's focus on this first diagram here, and let's get rid of some of the stuff that's labeled in this diagram right now. Let's get rid of everything except the wire and the magnetic field. Nothing's happening to this wire. It's not doing anything. It's not causing anything. Nothing's causing it to move. It's just sitting there. We've got a wire and a magnetic field that's just sitting there. There will be no effect on this wire right now as it sits there in this magnetic field. We do have an electron labeled in this diagram. There's going to be not just one electron in the wire. There's going to be thousands of electrons in the wire. We're labeling one just so that we can see it a little bit more clearly. This one electron, we're going to push upwards. But we're going to do it by pushing the wire upwards. Now, I don't care how we push the wire upward, whether we physically take our hand and push the wire up into the air, or whether it's steam that's rising and causing this wire to move upwards. As in the case of a power plant, steam rises, causes a turbine to turn. It doesn't matter. Bottom line is, something is physically pushing this wire upward, and it's not a magnetic force. Okay, something is mechanically pushing it upwards. So now we get this wire moving upwards. Now, understand what's happening here. As this wire moves upward, the electron that's in the wire also moves upwards with it. This is not an electric current per se, because we're physically just pushing these electrons up into the air. But it is a moving electron. When we have a moving electron exposed to an external magnetic field, it experiences a magnetic force. We can find the direction of the force on that particle by using the hand rule for deflection. So let's do that. Let's say thumb in the direction of the particle. I'm pushing this wire upwards, so let's stick our thumb upwards, indicating that the electron is also going upwards. Okay? Thumb upwards in the direction of the particle. Fingers in the direction of the external field from north to south. Palm points, which way is my palm pointing? Out of the page, out of the board. That means the magnetic force on this electron and all other electrons in this wire as well is pointing out of the page. What happens to an electron that experiences a force out of the page? It starts moving out of the page, right? Well, if this electron starts moving out of the page, it's flowing along the wire. What do we call that? When electrons are flowing through a wire, what do we call that? It's an electric current. So I've just generated an electric current moving electrons through a wire simply by pushing the wire physically with my hands or whatever, as long as it's exposed to an external magnetic field. If I leave the diagram as is, diagram A, then these electrons will start collecting down here. We get this potential difference between the two ends, a difference in electrical energy between the two ends because of this buildup of charge. But if I connect this end of the wire to a complete circuit, and maybe toss in a light bulb right there, then the electrons aren't going to stop at that end. They're going to go all the way around the circuit, and they're going to power that light bulb. Somebody in my period 2 class, in addition to somebody in my period 3 class, both classes said somebody asked essentially the same question. They said, well, isn't the light bulb going to go off, like pretty quick? Yes, it will go off pretty quick. It'll go off as soon as you stop pushing the wire through the field. As soon as the wire stops, the light bulb will go off. That's because there's no current produced. Remember we said we needed one of 3 conditions met to get a current produced. We need to move a wire through a field, we need to move a field relative to a wire, or we need to change the field. If the condition that's being met here is moving the wire through the field, as soon as that wire stops, the current's going to stop as well. The light bulb's going to go off as well. So how do we keep the light bulb lit? Don't stop moving the wire. Keep pushing the wire. Now, it's not practical to keep pushing it upward through the magnetic field because you're going to run out of space pretty quickly. So what you do is set up something that's pretty similar to the electric motor that we talked about yesterday. You have this armature. Pretend this piece of paper is my armature here, okay? Instead of a current going through the armature causing it to spin, what we're going to do is physically spin the armature. We're going to push the armature and make it turn mechanically. As it does that, the wire keeps moving through the magnetic field. We don't leave the magnetic field. We don't run out of space because the wire is rotating through that magnetic field. That's going to generate a current in that armature, and that's going to power whatever you need to power. An electric generator, a practical electric generator, is exactly the opposite of an electric motor. Instead of having a current through the armature causing the armature to move, we're moving the armature, causing a current to flow through the armature. Now, how exactly do we move the armature? How do we move that coil of wire? We can push it. You guys have probably seen in junior high school those hand crank generators, those little ones that you plug into light bulbs. You guys seen those? Turn them, the light bulb comes on. No? When I was a kid, back in the old days, when I was a kid, I used to have a light for my bike, but batteries were terrible back then. Batteries would last, and light bulbs were terrible as well. Light bulbs would suck so much power that your batteries would last. If you had a battery-powered light, it would last for maybe an hour, if that. So the way bike lights were back then, back in the day, back in the 1970s, they used to have this little thing that rubbed up against the wheel and turned as the wheel turned. So the wheel caused this thing to turn. As the wheel was turning, it caused a wire inside this little device to move relative to a magnetic field. That caused an electric current to be generated, and the light bulb would light up. The problem was when you stopped, what happened to the light? It turned off. Yeah, it turned off when you stopped because there was no longer a wire moving relative to a magnetic field. So we can pedal power. We can move this armature by pedal power. Just about every mass production power plant uses this principle as well, uses the electric generator as well. 80 or 90% of the power generated in Alberta is by burning coal. We burn coal, what happens? It makes a lot of heat. That heat boils water. What happens to boiled water? It turns into steam. What happens to steam? Rises. What do you have above that column of steam? A turbine. You basically have an armature. It spins as a result of the steam hitting it. That generates an electric current. What do you have in a hydroelectric dam? Same thing, except it's not steam rising that's causing the turbine to turn. It's water falling that's causing the turbine to turn. What do you have in a nuclear power plant? Well, you have an atom that you're splitting. You're not burning anything, but you're splitting the atom. That generates a lot of power. It generates a lot of heat. That heat boils water, creates steam. Steam rises through a column, turns a turbine, generates electricity by moving a wire relative to a magnetic field. Even with wind power, the wind comes, blows the turbine, moves a wire relative to a magnetic field, generates electric power. The only real practical way of generating electric power on a fairly big scale is solar power. Sorry, the only one that doesn't rely on this principle is solar power. It works on a completely different principle than this. And we'll talk a little bit more about that as we go on in the year in Unit 5. Electromagnetic induction, the generator effect. Move a wire relative to a magnetic field, you're going to make a current. It's as simple as that. I'm going to give you a few questions to work on for homework that's related to this stuff that we've been talking about. I want you to do the questions on page 613, questions number 1 to 3, and 7 to 11. 1 to 3, 7 to 11. We're going to move on and do a little demonstration and talk about one more little concept here right now. If we have time at the end of class, and we might, then you guys can get a bit of a head start on this. If not, please do these 8 questions for homework tonight. We just saw the demonstration of dropping the piece of steel through the copper tube and then dropping the magnet through the copper tube. When we dropped the magnet through the copper tube, it went down, it fell at a much, much slower rate than the piece of steel did. The piece of steel accelerated downward at 9.81 meters per second squared. The magnet accelerated downward at a much, much lower rate. Why is that the case? Copper is not a ferromagnetic material. The magnet isn't attracted to the side of the copper. So that shouldn't have any bearing. Well, it has to do with something that we call Lenz's law. Here's what happens. When you move a magnet, when you move a magnetic field through a conductor, and that's what copper is, it's a really good conductor, you generate an electric current. Hence, Michael Faraday and Joseph Henry taught us that in 1832, I believe it was. You move a magnetic field through a conductor, you generate a current. That was one of those 3 conditions, remember? You got a conductor, you got a magnetic field, you move one of them, you're going to produce a current. Now, that current is really, really small. It's so small that I can't even feel it. When I'm holding onto this copper tube, there's no way I'm going to feel this electric current that's generated there. But it's there. Now, this electric current that we've just generated is going to make its own magnetic field. Oersted taught us that in 1819. So there's an electric current in this conductor now that produces its own magnetic field. Now we got 2 magnetic fields. We got the magnetic field that I dropped through there, the magnet, and we got the second magnetic field that was just made from the electric current. Those 2 magnetic fields will always, every single time, act to oppose the motion of whatever's moving. So if you drop a magnet, the magnet is going to be, the motion of the magnet is going to be opposed by this magnetic force. If we somehow held the magnet and dropped the copper tube, then the motion of the copper tube would be opposed. It's always going to be opposed. Now, why can't it ever be helped along? Why, when I drop this magnet down there, why does it accelerate at 1.5 meters per second squared as opposed to, say, 13 meters per second squared? Why can't it go faster than gravity? Why is it always going to go slower than gravity? No. If it was attracted, if the motion wasn't opposed, if it was helped along, it would violate the law of conservation of energy. Imagine the implications of that. You make this thing horizontal, this copper tube horizontal. You put a little magnet in there. You give it a bit of a push. As opposed to its motion being opposed, instead of its motion being opposed, it's helped along. So we give it a bit of a push. What happens? It gets fired out the other end. That can't happen. That magnet, as it's fired at the other end, would have a tremendous amount of kinetic energy that didn't come from anywhere. Energy would have been created from nothing. Me putting the magnet in there, giving it the tiniest bit of a push, would cause it to be fired out the other end at who knows what speed. We can't create energy from nothing. That's fundamental. That's the law of conservation of energy. So if there's a force between these two magnetic fields, the one that was made by the electric current and the one that was already there, it's got to be an opposing force, not an attracting force. It's got to oppose the motion as opposed to helping the motion. When a magnetic field, we'll call it magnetic field number 1, and a conductor move relative to one another, doesn't matter whether it's the magnet or the copper wire, the copper tube, we're going to get a current produced in the conductor. That's Faraday. That's what we learned earlier today. Now there's an electric current there that generates the magnetic field. We'll call that magnetic field number 2. That's Ørsted. We learned that near the beginning of this unit. Here's the big part of Lenz's law, though. Magnetic field number 2 will always act with magnetic field number 1, always, to oppose the motion. It has to oppose the motion, because if it didn't oppose the motion, if it helped along the motion, then the law of conservation of energy would be violated. You'd have all this kinetic energy that came from nowhere. And we know, we learned back in Science 10, that just can't happen. The law of conservation of energy forbids this kinetic energy coming from nowhere. So it must be opposing the motion as opposed to helping along the motion. That's Lenz's law. And that is our unit. We'll spend some more time tomorrow doing some review, doing some applications of some things, going over some questions, answering your questions, and then we'll have ourselves a unit test on electricity and magnetism on Monday.